Hello guys, this is CodeNCode and this is fourth lecture of fast Fourier transform, which is basically part 2 of lecture 3, right? So let's see what we are going to learn in this lecture. So till now, till the previous lecture, what we have established, let's go through that. So a polynomial of degree n requires to be evaluated on n plus 1 points. To optimize the evaluation algorithm, we need to evaluate the polynomial on positive negative pairs, right? It saves us a lot of time. Now, polynomial, while evaluating, what we do, we break it into PE and PO, right? Even and odd terms polynomial, and then evaluate those recursively. This gives us an log n solution, right? P and PO will be evaluated on the squares of point on which P needs to be evaluated, right? If P needs to be evaluated on 1 minus 1, 2 minus 2, PE and PO only needs to be evaluated on their squares. That means 1 and 4, right? We have established that. That's why P and PO will be only evaluated on half number of points, the fifth one. The issue that we were facing is that when we go deep down the recursion level, uh, the positive negative pair we didn't get those, right? Just after the first level, right? So what we said that a complex number, that is roots of unity to be precise, can actually solve that problem. And let's see how. So let's learn a little bit about roots of unity. So the solution of x raised to power n is equals to 1, right? And it will have n equidistant points on unit circle drawn on complex plane. So this is my complex plane, right? So this is the complex axis, this is the real axis, and then you have a circle of unit length, right? Unit radius. Now the solution, that is roots of this equation, lie on this circle and they are equidistant, right? So starting from 0 degree, for example, the first root, as you can see, there are four roots, right? This and this. These are the four roots. Starting from the first root will always start from 0 degree, and each root will have 360 by n degrees between them, right? Now, for example, this solution that you see, this is actually a solution of x raised to power 4 is equals to 1, which has solution 1 minus 1, I minus I. So I have drawn all of those four here. And if you see, all of those roots are 90-degree apart, because n is equals to 4 in this case, and 360 by 4 is 90. So each of those roots are 90-degree apart. So this is a little bit about roots of unity. And how it's going to help us? We need a set of numbers. When we square them again and again and again, each time we get positive negative pair, right? And not only that, when we scare them, when we square them, two of those points, right, from let's say ith recursive level, when we square 2 points there, they are pointed towards, or they are mapped to only one number in the next recursive level, right? That's why we, in the next recursive level, we only evaluate the polynomial all half number of points, right? So you see, this is solution of x raised to power 8 is equals to 1. As you can see, I have plotted 8 different roots. So if you see, for even n needs to be even, x raised to power n is equals to 1 has exactly n by 2 number of positive negative pairs, which are separated by 180 degree. You can actually prove it very easy, right? You can prove it using Euler's formula. That is, a complex number can be represented as e raised to power I x, right? Where x is the theta, so angle. So it is equals to cos x plus I sin x, right? Now, what we see here, using this, actually you can prove that, and two of the roots which are separated by 180 degree, that means pi, and when n is even, there will be roots that will be separated by pi. You can actually prove that they will always form positive negative pair, right? Since we are not going deep into the complex number theory, I won't be proving that, but you can do it easily, right? Yeah, so the thing is that if n is even, the solution of this equation has n by 2 positive negative pairs that are separated by 180 degree. For example, this and this, these two are vertically opposite, right? And they are positive negative pair. For example, this and this and this, and this and this, all of those form positive negative pair. That is one of the property that we wanted, right? We want to evaluate polynomial on positive negative pair. Complex numbers, that means roots of unity, provides us one thing, right? And yeah, each angle you can see is I mean, two of the consecutive roots of unity are separated by 45 degree, because 360 by 8, because n is 8 in this case, right? So 2 pi by 8 will be the delta between consecutive roots, right? And times 0 times 1 times 2 dash 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 times 7, because there are 8, 0 till 7, this will be the angle of each root. So times 0 times 1 times 2 times 3 dash 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 times 7. So these are all of the angles of roots of unity, and put these angles here, you'll be able to get their actual coordinates or actual complex number, right? So one thing is clear, these complex numbers, especially the roots of unity, actually form positive negative pair. That what we are looking for, one thing. Second thing is, when we square them, two of the numbers must be pointing to a singular number in the next recursive, right? So we are going to do that. We are going to see how it helps there. First of all, just want to give you a representation of ith root of unity, or kth root of unity. So kth root of unity, where k ranges in 0 to n minus 1, of course, because there are n roots, can be represented as, using Euler's formula, of course, a is for 2 pi by n times k, and I will be there because this is an imaginary number. So 2 pi by n times k, right? And this is also represented using w, very commonly represented, right? So you can represent each of these number as w is raised to the power 0, w is to the power 1, 2 dash 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 to n minus 1, right? This is just another representation, nothing special here. Where w is for k is simply 2 pi by n times k, right? Yeah, so this is another representation, because we are going to use w representation a lot. So let's have a look at these. So these are roots of unity when n is equals to 8, and these are roots of unity when n is equals to 4, right? So just to recap, so if you want to evaluate a polynomial on n points, we evaluate that polynomial on nth root of unity, right? So one thing we have established, that roots of unity occur in positive negative pair. The second thing we want to establish is that when you square two roots of unity, they point to a single root of unity in the next recursive level, right? So let's say we want to evaluate polynomial on 8 points. In the next recursive call, we will evaluate PE and PO, right, on 4 roots of unity, right? So what we want to prove is that when you square two of these points, it map to a single point. That's how, when you are evaluating polynomial on 8 points, in the next level you only have to evaluate that on 4 points, right? So let's prove that. So if you see, when you square these numbers, when you square this and this, you actually get this and this, right? When you square it, you multiply 2 in the power of it, right? E raised to power, already we have this. When you square the whole number, you are basically multiplying the power. So 2 pi by 8 just multiply by 2, you will get 2 pi by 4 times I times 0, 2 pi by 4 times I times 1, 2 pi by 4 times I times 2, and so on and so forth, right? So first half number, when you square them, you directly get, they are directly mapped to the next roots of unity, right? One thing. So we have to somehow prove that these number also point to these, right? What you can do is this. Actually, when you square this, it points to the first number. When you square this, it points to the second number, and third and fourth. How? Let's go with. Okay, so this, if we see, I'll explain in a moment. First, let's see this. So the power you see here is two, sorry, we'll start, we'll talk about the blue ones only, the remaining numbers which come after the half points we have done, right? So 2 pi by 8 times 4, right? 5, 6, and 7, 8. That's what we have here. When you multiply these number by 2, you will have 2 pi I by 4, right? Times 4, 5, 6, and 7. That's I have here. 2 pi I by 4, 4 times 4, 5, 6, and 7, right? But why have I written them as 4 plus 0, 4 plus 1, 4 plus 2, and 4 plus 3? 4, first of all, is n by 2. So instead of writing 4, you could have written n by 2, plus 0 plus 1 plus 2 plus 3 is the same thing, right? Why I have written is that when you multiply 2 pi by 4 with 4 and 0, you will get this 2 pi plus 2 pi by 4 times 0, 2 pi by 4 times 1, 2 pi by 4 times 2, and 2 pi by 4 times 3. This is what you get, plus 2 pi, right? So just one thing, e is raised to a certain power, which is nothing but angle. When you add 2 pi into an angle, right, that means 360 degree, you add to a certain angle, its value doesn't change. Theta plus 2 pi is still theta, right? So 2 pi plus 2 pi by 4 times 0 is essentially 2 pi by 4 times 0, which is what? This 2 pi by 4 plus 0. Sorry, 2 pi by 4 times 0. That's why this number maps to this. Similarly, it will have 2 pi by 4 times 1, which is square of this number maps to this, and this and this, right? So we have proven that first half number, when you square, they directly map to the next set of roots of unity. The second half, when you square it, they also map to the next set of roots of unity, right? And here I have taken a specialized approach. You can take a general approach. Instead of 4, you just put n by 2 here, and then you'll be able to generalize a formula. I just wanted to take an example because that is easy to understand. And again, this is not a complex theory class, so of course I'm not dealing into detail of this, but I still tell you how you can actually prove it. Just instead of 4 plus I, you put 4 plus k, you put n by 2 plus k, and you will be able to prove it generally, right? Now talk about this. So if you see, kth number and n by 2 plus kth number are actually mapping to the same number, right? So this and this will map to the same number. First and fifth will map to the same number. Second and sixth will map to the same number. Third and seventh will map to the same number, right? So what does it tell you? That this and this are positive negative pair, right? They are positive negative pair. They're separated by 180 degree, because after half you get to the 180 degree, right? You'll be able to prove it easily. So basically, k and n by 2 plus kth number actually form the positive negative pair, right? When both of those are squared, they reach to the same number. So we see that roots of unity provides that both of those properties that we were looking for. First, they appear in positive negative pair. Second, when you square first set of roots of unity, they each two number from first set of roots of unity maps to sorry, maps to the single number in the next set of root of unity. That's exactly what we wanted, right? So roots of unity provides us both of those properties. That's why instead of going with real number, we'll move ahead with the imaginary numbers, right? And this is how we are going to solve evaluation problem using roots of unity. Now our recursion doesn't break, and we'll be able to achieve n log n runtime, right? Okay, so what have we learned about the properties of roots of unity? That when n is even, x raised to power n is equals to 1 has exactly n by 2 positive negative pairs. One thing. Second, x raised to power n r squared, when roots of x raised to power n r squared, we get roots of n by 2, right? We get roots of x raised to power n by 2, that we have seen, right? And then ith and I plus n by secondth, these two numbers form a positive negative pair. We just seen it, right? Kth and n by 2 plus kth number, they form positive negative pair. Yeah, so these are the things that we have learned about the roots of unity, and this gives us the freedom to use these to evaluate polynomial in n log n time. Now if we talk about the pseudocode or the FFT implementation, how it should go, and if you remember this formula, in the last lecture we have learned it, right? In the last few lectures we have learned this formula. So using this formula and the knowledge that we have gained so far about this, I'll tell you how you can evaluate P using PE and PO, right? So how FFT works is that you basically divide P in PE and PO, make a recursive call on PE and PO on n by 2 numbers, right? PE and PO now are evaluated. Using the result of PE and PO, we have to build the result for P. How we do that? Using this formula and this knowledge. I'll show you how you can do that. All right. So let's talk about the pseudocode. So basically we need to evaluate P on W is for 0, 1, 2, 3, 4, 5, 6, and 7. And mind you, w raised to power 0 and w raised to power 4 have the same value. They are just positive negative pair, right? Because ith and I plus n by second numbers are positive negative pairs, right? So now, uh, using this formula, we are going to evaluate all of this polynomial, right? P. And since we already make a recursive call to PE and PO, PE and PO are already evaluated, right? So how we are going to utilize the values of PE and PO to form P is this. First of all, we need to evaluate P on D and minus D. That means positive negative pair. So positive negative pairs of P are at ith and I plus n by second position, right? Basically 0 and 4 will be evaluated together. So P of I and P of I plus n by 2. These two will be evaluated together. That's why we are running a loop till n by 2 only, right? So till by n by 2 only, for one more reason, because PE and PO are evaluated till half the points. If this is evaluated on 8 points, this is evaluated only on 4 points. That's why we are running a loop till 4 only, right? Now, so these two are positive negative pairs, and positive number, basically polynomial P is evaluated on D using PE and PO of this formula. So PE of ith times W raised to power I times PO of I, right? Why is W raised to power I? Because when I is equals to 0, P needs to be evaluated on W raised to power 0. That's why that power. When I is equals to 1, W needs to be evaluated on W raised to power 1. That's why here. So you might want to ask why here, when I'm evaluating basically P of 4, why W is not raised to the power 4? Because, right? Because 0 and 4 are evaluated together. If I is equals to 0, this will be evaluated as W raised to power 0, which is fine. But this is basically W raised to power 4. This needs to be evaluated on W raised to power 4. Why this negative sign? And why this negative sign, as well as why W is not raised to the power 4? Because W raised to power 0 and W raised to power 4 are having the same values, just reverse the sign, right? They're just positive negative pair of each other. That's why W is power 0 and W is power 4 are in basically the same, only the sign flips. That's why we have minus sign and we are still going with W is power I, right? So using this formula we have established a lot earlier, right? So using this formula, this is how you can actually combine the result of PE and PO to evaluate the original polynomial P, right? And now you can actually, if you go through any code, you'll be able to understand how the whole thing works, right? Don't worry, in the next lecture, of course, I'm going to implement the whole thing, and everything that we have studied so far, we are going to actually utilize that. This thing, everything. Then you will be able to understand it more clearly. Right. So this is how you implement FFT. This was the most important part to, combine the recursive results of PE and PO. This is how you do it. All right. So yeah, this is how you implement FFT. The pseudocode is there. In the next lecture, we are going to implement it. Right. Now, let's learn about inverse FFT, because what we have done so far, see, we are given two polynomials A and B, and we have to multiply those. These two are in coefficient form, which is tough to multiply. So what we are doing, we are applying FFT and converting polynomial A and B both into value form, right? They were in coefficient form. We have converted those to polynomial form. Polynomial value form. Now that we have value form, what we can do, we can directly multiply each value, each corresponding value, and we'll get a new polynomial, that is C, right, in the value form. But we don't want the value form, we want the coefficient form of polynomial C, the resultant. Now we need to do something called as inverse DFT or inverse FFT. That is the process of converting value form into coefficient form. How we can do that? It is surprisingly easy to understand. See, so basically, when we are doing FFT, what we are doing, we have this coefficient. Basically, this is the polynomial we have. We are evaluating this polynomial using power, using roots of unity that I have represented here. W is power 0, W is power 0, the first one. This is basically matrix multiplication of what we, matrix representation of what we have just done now. We have evaluated the polynomial and powers on powers of W. right? So you take the first row, multiply with the first column, you get W0. You take the second row, multiply with the first column, you get W1, so on and so forth, right? So this is evaluation process. You multiply these two matrices, you get the resultant matrix, right? Basically, multiply evaluating the coefficient form to give us result in the value form. Now, what inverse DFT does, sorry, inverse FFT does, is that we are already given the value form. We want the coefficient form. How you can do that? Just send this matrix that we have just used, right, onto the other side. And when you send a matrix to the other side, you have the inverse of that matrix. Multiply inverse of that matrix with the value form, and you will get the coefficient form, right? And surprisingly, the inverse of the matrix of this matrix is very much similar to the original matrix, right? First of all, we have multiplication factor of 1 by n, right? And then if we see every element of previous matrix that we have used to evaluate a polynomial, both of them, the values are same, except for one thing. Here we have negative powers, right? Powers means angles. So basically what we have to do, we have to perform the exact same thing. Nothing changes. This matrix is the same, and we have again a value form. Just multiply this with this uh, value form, and you will get the coefficient form back, right? So we are doing the exact same multiplication. What we are doing, we are performing multiplication here on the left hand side in the FFT. In the inverse FFT also, we have to perform multiplication. Instead of performing multiplication with positive angles, what we are doing, we are performing multiplication with negative numbers, right? Negative powers, I should say. And once you get the result, each value must be divided by n to get the coefficient. So this way you can what you can do, you can again utilize FFT. Instead of multiplying with positive powers, you multiply with negative powers. How? This is very easy. When I show you the implementation, it's literally when you're calculating the angle to calculate W is bar 0, W is bar 1, so on and so forth. Whatever value you are, whatever calculation you are doing here, just multiply it with -1. That's it. FFT, inverse FFT, because the whole thing is same. The whole matrix is same. So whatever you are doing in FFT, you have to do in inverse FFT only with negative power. That's it. And of course, once you get the result, divide each number with n, then you will get the result. Right? This is the inverse of this matrix because that's what we wanted. Right? So this is inverse FFT. So yeah, this is how FFT works. The only thing left for us is to implement FFT, implement inverse FFT, and you'll see that both of the implementation matches like 90%, right? 95%, I should say. Basically, copy paste the same code, change one thing with minus, and that's it, done. Yeah. So we have learned what is FFT, how it works, how roots of unity help us achieve and log in evaluation time basically for FFT, right? And we have seen the pseudocode of how it works. Now, in the next lecture, what we are going to do, we are going to implement this pseudocode that we have written into an actual working code, and we'll see that yes, and we'll make sure that, of course, after performing certain tests, that this actually works. And after that, next to that lecture, we are going to solve 2 or 3 problems ranging in multiple difficulty levels, starting with easy, medium, and hard. I'll try to go till the hard concept itself, FFT, right? So yeah, this is it for this lecture, and see you guys in the next lecture. Until then, just keep coding. Thank you.